All right, so yesterday we were talking about these two equations for torque. I kind of see these two equations as cause and effect. All right, this equation is what causes your torque, right? You're applying some force to your object, some radius away from your pivot point at some angle. Okay, and then the result is your object, which has some rotational inertia, undergoes some angular acceleration. Okay?
Does it have inertia without?
Say that again, does it have inertia what?
Without.
Yeah, absolutely. In the same way that an object has regular inertia without moving. My water bottle has inertia right now because of its mass.
Wait, does it minus the...
It's a resistance to a change in motion. It doesn't have to be moving to be resisting motion. Good?
Yeah.
All right. So, as I was trying to say yesterday, and I was hemming and hawing about whether or not we had time to get through it, most of the problems are going to be some combination of these two equations. All right. So, example 2 is a great example of that. Let me run through example 1, though, just so you can kind of see how it works. All right. So, here we go. So, this one, it says car's tires have a radius of 33 centimeters. I'm going to right away just convert that to meters. And then they have an inflated mass of 10 kilograms. Find the net torque needed to accelerate the car from an initial velocity of 0 to a final velocity of 60 miles per hour in a time of 6 seconds. All right, so this actually has elements of, oops, it's not trying to do, kind of everything that we've done so far. Okay, so it doesn't give us any information about the force that's being used to accelerate the tires. All right, so this equation doesn't seem like a great candidate to use to find the net torque. So I'm going to see if this helps me a little bit. Okay. So in order to find my net torque, I need to figure out what I is, what's the rotational inertia, and figure out what alpha is. Okay? So I, remember, that's a property of the object. And the text of the problem here tells us that we can treat the tire as a solid cylinder. Okay? That's a little bit of an oversimplification because technically the density of a tire is not uniform, but we can approximate. So that means for us, I is, well, you look at that sheet and find the rotational inertia for a disc or a cylinder, and it turns out that it's 1/2 mr squared. Does anybody need me to go back and show where I got that, or are we okay? Okay. Yeah, it's just on the chart. So keep in mind, you guys, this has thrown a few people off. A disc and a cylinder are treated the same way, okay? Because the size of the disc or cylinder this way doesn't matter. So even if this thing was super tall, you would still use the same equation to calculate the rotational inertia this way. Okay? Say that again. Well, yeah, I mean, I think usually when you say disc, somebody pictures it being flat, like a record. And usually somebody pictures a cylinder as being like a tin can. It's a little bit taller, I guess. But, all right. So let's plug in our numbers. Let's see. So our I is going to be 1/2 of the mass of this thing. So 1/2 of 10 kilograms times our radius, which is 0.33 meters. Don't forget to square it. And that gives you a number that I have written down somewhere. It's probably quicker for me to just recalculate it. Where's my stupid paper? So what do we got? 5 times 0.33 squared. Oops. 3 squared. Well, it would be faster if I knew how to use a calculator. Oh my gosh. 5 times 0.33 squared. There we go. So it gives you 0.5445. What are the units again, you guys? What do you get when you multiply this covered up? You get kilogram meters squared. What happened? Oh, gotcha. Yeah, I hear you. All right. So everybody good with that? So again, that's a property of the object. That's because these wheels are cylinder-ish. That's the rotational inertia. All right. So now we need to find our alpha. So here's my recommendation, you guys. Most of the values we're given here are linear values, right? But we need to find angular acceleration. because we're given mostly linear values, let's do our calculations using linear values and then use a jumper at the end to jump from linear to angular. So here we go. So this 60 miles an hour, if you calculate it, turns out to be 26.8 meters per second. Everybody okay with that? Just back to label, right? Dimensional analysis, sorry. So then A is V minus V naught over T. So here's our V, here's our V naught. T is 6 seconds. So divide it out, and you get, how did I already lose my calculator? 6.8 divided by 6 gives you like, we'll just call it 4.5, let's say. 4.5 meters per second squared. Cool? All right. And then remember, you guys, this is actually the acceleration of a car, right? Okay, but that also corresponds to the linear acceleration of a point on the outside edge of the tires, right? Okay, so that means that we can use that then to find our alpha by using one of the jumper equations, right? So A equals alpha r means that alpha is A over r. So there's our acceleration, 4.5 meters a second squared. Our radius is the 0.33 meters. Divide it out. It gives you like 13.5 radians per second squared. Cool. Right. So this is the rate at which we want the wheels to accelerate angularly. This is their rotational inertia. So the net torque is just the product of those two things. So if you multiply these two guys, you get the torque that I told you get. Somebody's calling. All right. So net torque is I alpha. Here's the I. Here's the alpha multiplied out, and you get about 7.37, 7.4, something like that meters. Cool, you guys? All right. So that was basically just a demonstration of how you use that I alpha equation. The next example is a little bit more involved. So, are there any questions with example 1 before I jump ahead to example 2? All right, let me dig up my notes so that I'm not. Hello. This one. Thank you for being patient. Oh, no, must be this one. Okay. All right, so example number 2. I'm just going to do part A. Part B is the exact same thing, but it would be worth your while to, try it. Okay? All right, so it says Roy is attempting to lift a large piece of plywood that's sitting on the floor. Okay, so we've got, a big plank that's sitting on the floor. All right? It says the uniform board is 1.5 meters wide, 3 meters long, and it's got a mass of 60 kilograms. He grabs the short side of the board and lifts up with a force of 300 newtons. What angular acceleration will this give the board initially? All right, so the idea is you've got this piece of plywood sitting here. Okay, he's going to grab the short side of the board like this and lift it. Okay, so he's causing it to rotate, right? Does that make sense? All right, now there are 2 forces on the door, or on the plywood rather. What are the 2 forces? Good, gravity and him, right? So, his force we know is 300 newtons, right? What would my lever arm be? What's the length of my lever arm? 3 meters, right? Because he's grabbing the short side of the board, so that means that this distance to the pivot point is 3 meters, right? Good. Now, what about gravity? How do I treat gravity? Very good. Yeah, you treat it as though it was the whole mass of the board was located right at the center of mass of the object. Okay, so that was, I told you guys when we did center of mass last chapter, I said I thought that was a weird place to put it. Here's where I think it belongs, is when you talk about torque. Okay, because when you calculate the torque generated by an object's weight, you treat the force of gravity on the object as acting at the object's center of mass. Okay? So that's going to be big for this. Okay? So that's kind of a general overview of where we're headed. There was a question?
I got a question. So whenever I file with that, they always get this back force.
Oh,
That
yeah.
comes into play. And follow-up question.
Yeah,
what's
we're not going to calculate that.
What's on your hands?
Oh, I was doing a thing with gravitational and kinetic energy. Right? Gravitational and kinetic.
Um,
Okay, all right, so let's do this. So let's make ourselves a drawing. So here's the plywood sitting on the floor, right? So I know that this side here is 3 meters long. I know that this side here is 1.5 meters long. Roy's going to grab this side and lift up. So let's draw in our force of Roy. 300 newtons. Notice that's going to determine my pivot point, right? It's going to determine my axis of rotation. So that's probably worth kind of marking. I usually use a dotted line or just like a dot or something. There's my pivot point or axis of rotation, whatever you want to call it. Good? All right. And so then the distance that's going to be associated with that force, I'm going to call it dr, just so that you know that that's the distance that goes with this force, is going to be 3 meters, right? Everybody good up there? Up to there? All right. Now, there's another force. We know that the board has a mass of 60 kilograms. So that means my force of gravity is going to be 60 times 9.8, so 588 newtons. Follow? I'm going to put that at my center of mass. So COM is what that little X there represents. Okay? So here's our force of gravity. It's 588 newtons. And then the distance associated with gravity. Oh, I'm sorry, I did it. I told you guys this was going to happen. I used D instead of R. Torque is R times F, and I just used D. Is that going to mess anybody up? Do I need to go change the D's to R's? Sorry. Still used to using FD. So what should this distance be, you guys? 1.5 meters, right? Please notice, it's just coincidence that this is 1.5 and this is 1.5. That wasn't intentional when I wrote the problem. I need to tweak that. Everybody good? All right, so we got to calculate our net torque, right? So our net torque should be the torque from gravity plus the torque from Roy. So the torque from gravity is going to be the force from gravity, 588 newtons, times the distance for gravity, which is 1.5 meters. And now we got to use the right-hand rule to determine a direction. Is it a positive or negative torque? So you guys decide, because you guys use a different method than I do. I want to make sure we agree. All right, I see some of you struggling with it. Here's how I would do it. I would lay my fingers along, because it's D cross R, right? So I'd lay my fingers across D, and then curl my fingers in the direction of the force. So that points into the board, which means this is a negative torque. All right? In just a minute, we'll do the other one. So to do the blue one, look, I can't bend my fingers up because I'm not double jointed. So I got to flip my hand over and now curl them up. So that one's going to point out of the board. Okay? So this torque, the blue torque, is going to be positive. So here's the green. And over here we'll write the blue. So this one's going to be 300 newtons times 3 meters, and it's positive. All right? Now, if you want, if you're unhappy with the whole right-hand rule thing, at some point you need to learn it. But for now, you can just think in terms of clockwise, counterclockwise. Which into the board is always negative. Into the paper is always negative. Yeah, it's like on your paper, it's like thinking of it as down. Cool. Yeah.
I just realized like why the curling one and this one, this thing works, because this is like the same thing as curling, because it's where it starts and you point to where it needs to be.
I can never remember which finger is which is why I like this, because it seems more active to me as opposed to memorizing this finger means this thing. So I can never remember if it's this or this.
It doesn't matter.
It's
As long
entirely
as
relevant
you
which
got
one
one
you
you
use.
use.
Say that again.
It's entirely relevant which figure you use. So will end up the same.
Oh, really?
But, yeah, see, you say like your force is pointing this way and like your axis of rotation is down here, not here, then you can switch it whatever way you want. You can't do it other ways. So
Gotcha.
Your thumb's perpendicular no matter
But
what.
it matters which,
Vectors.
whether you do R cross F or F cross R, so which finger do you do first?
No,
No matter which
it
one
doesn't
you
matter.
point,
It doesn't
you're
because you're still across.
Say that again?
If you're ever pointing like up, then your thumb's going this way, but like up with this way, your thumb's that way. Like your thumb always goes.
What do the different vectors represent, I guess, is what I'm asking.
This is the point. Almost the first one. And then the.
Oh, okay.
So it's
I
the
see.
same thing.
Gotcha.
It's the same thing. Instead of a curl, it's just a slit.
Gotcha.
Like a curl.
Okay. All right. Well, but so anyway, so we all agree. Does everybody have a method that works for them? All right. So, old dog. All right. So, all right. So let's finish this up. So my net torque here. So my net torque here. This ends up being negative 882. Yes. Final answer. Plus, oh, I guess I should put Newton meters. Plus 900 Newton meters. So I get 18 Newton meters of net torque. Cool? Questions on that? We're not done, but everybody okay up to there? All right, so notice, to find my net torque, I basically used the FD equation, right? The question wants to know the angular acceleration, so I gotta find alpha. So, now that I know my net torque, now I can use, squeeze it in here, net torque equals I alpha. If I can find my I already know my net torque, so I can find my alpha, right? Alpha? All right, so you guys have all this written down. I'm going to erase part of the board. Is that cool?
Yeah.
Okay, so, actually, I guess I can erase. Well, we'll leave it. All right, so, I. So to find our I, we got to look at that sheet, right? So what kind of shape is this? Yeah, it's a rectangle, right? It's three-dimensional. So I guess there are two rectangles on the sheet. There's one where the pivot point is in the center, and there's one where it's at the end, right? You want the one where it's at the end. Okay? Which dimension? So here's the equation. It's 1/3 m. For some reason, the sheet has a squared. They've got the rectangle as being a by b. You know, instead of length times width, they used a and b. Which dimension do you think a is? The 3 or the 1.5? The 3, right? Because that's determining the sort of the radius of rotation, right? Does that make sense? The depth this way does not matter. It's just this. So we're going to get 1/3. The mass of the door was, what, 60 kilograms? Our A is 3 meters. Don't forget to square it. Multiply all of this out, and you get 180 kilogram meters squared. And so now we can find our alpha. Right? Alpha is going to be net torque over inertia. So we get 18 over 180. Let's see what our units work out to be here. The 18 was the torque, so that's Newton meters. And then we're dividing it by kilogram meters squared. So if you do this, so remember a Newton meter is a Newton is a kilogram meter per second squared. When you multiply it by meters, you get kilogram meters squared per second squared. When you divide, everything cancels except for the per second squared, and the radians magically appear because of the derivation of this equation. So you end up getting 0.1 radians per second squared. Cool? Now, assuming that he continues pushing straight up, is that torque going to be constant? Is that acceleration going to be constant? No, because as it tips, your force no longer is 90 degrees, right? And so that's why I wrote, what angular acceleration will it give the board initially? Okay, that acceleration is going to change, unless he, well, even if he rotates his force, right? Because gravity will always be straight down. So.
There be like related bringing around.
Yeah, it gets ugly there, but yeah, I haven't seen any like that, thankfully. All right, good. Questions, issues, concerns? Okay, cool. So, I think you guys know enough to do most of the 8.4, 8.5 assignment. I was looking, there might be there's one problem that has like a pulley that I think if you guys think you guys can figure it out. So yeah, so sorry, I keep saying 8 because all my other classes are in chapter 8. So why don't we tentatively make the 10.4, 10.5 stuff due, you want till Tuesday? So you not do the day right after break. All right. All right, so let's do that, and then we'll take time today to finish up the 10.1 stuff, and then we'll see what's going on Monday, I guess. All right. Cool. All right. Sorry to give you homework for a break, but we're quickly approaching the AP test. All right. So what's up there? We got let's say 7, 18, 24, and 27. What's that? 3? Oh, 3, 8. Cool. Sorry, there's always a glare, so I can read it. Okay, so shoot, I was not smart. Grab a copy of that. Thank you, Doug. All right. So first of all, I guess the concept questions. I hope you guys noticed the answers were in there. You guys notice that? That I'm going to try to put those in there. Do I need to go over any of the 3 concept questions? 1, 2, or 4?
These 2, I just didn't understand what it meant when it said how for data. Just go over interest too, I guess.
Just 2?
Sure. Then I can try it.
Okay. All right. So number 2, you've got a graph. Sorry, I should have brought it up. I'm not as well prepared today as I should be. So one of them is a graph that looks like that. That's graph number 3. Graph number 2, or number 1 rather, looks like this. Ish. And then there's another one that looks like this. This one's 2. This one was 1. Our axes here are time, so somehow we're allowed a negative time value, which is annoying. I don't know why they do that, but whatever. Okay, so those are our 3 graphs. All right. So basically, you guys, you can treat this the same way that you would treat a regular position time graph. Okay. So let's look at graph 1 for a minute. If this was position time, like meters versus time, what would this mean? Decreasing position, right? So it would be moving backwards and slowing down until it stops, and then going forward faster and faster and faster, right? So this is the exact same thing. This is a wheel spinning in a negative direction, slower, 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 stopping, and then spinning in a positive direction, faster and faster and faster and faster. Okay? So it's, let's say, negative direction is clockwise. So it's spinning in a negative direction, slowing, slowing, stopping, and then going in a positive direction, faster and faster and faster. That's the green graph. Cool? The blue graph is the same thing, except it's just a little bit later in time, right? Does that make sense? Okay? What's the red one doing? The opposite, right? So, okay. So, with that in mind, let's answer the questions here. Let's see. So the graph to the left shows a plot of angular position versus time for 3 cases in which a disk is rotated like a merry-go-round. In each case, the rotation direction changes at a certain angular position, theta change. So for the green one, how would I identify theta change for the green one? Where do I look on the graph? I find the minimum and then go to which axis, down or across? That's theta change, right? Because that would be the angular position at which it turns around, right? That's a little bit tough to visualize because I think, so if it was a number line, that would just mean that, we got to a position of, maybe we got to a position of 3 and then stopped and came back, right? Does that make sense? All right, so this is saying we got to a position of whatever, pi over 2 radians, and then turned around at that angular position. Okay? So for each case, determine whether theta change is clockwise or counterclockwise from theta equals 0. Well, theta equals 0 would be here. So clockwise from there would be a negative, and counterclockwise from there would be positive. So this is counterclockwise from theta equals 0, right? Because it's a positive angular position, right? This one is hat theta equals 0. And this one is, again, counterclockwise from it because it's a positive position. Does that make sense? Philip, you good? Then it says, for each case, determine whether omega is 0 before or after t equals 0. Well, this is before t equals 0. This one, if you look at the graph on the paper instead of mine, it's at t equals 0. And this one's after t equals 0, right? All right, and then finally, C, determine whether your alpha is positive, negative, or 0. All right, so let's do it for the green one. My starting angular velocity is positive or negative? Negative, right? Because that's a negative slope, right? And then it becomes less negative and eventually becomes positive. So that's a positive angular acceleration. Say that again? Free derivatives like sine and cosine stuff? No more than anywhere else. Clearly. All right, good, you guys? Cool. And let's see. So number 4 is similar to that. Does anybody need me to say anything about number 1? Okie dokie. Cool. All right, so that was number 2. So here we go, number 3. Problem number 3. Oh, the buttered toast problem. I like this problem. So this one, honestly, is more just like problem solving than it is physics, to be 100% honest. There's a little bit of you gotta know your radiance. Yeah, all right, so here we go. We got a slice of buttered toast. It's accidentally pushed over the edge of a counter. So let's draw ourselves a little counter. Let's give ourselves a slice of buttered toast. So here's the bread, and here's, then we'll make the red side the butter, okay? Cool? All right, so buttered toast is accidentally pushed over the edge of the counter. It rotates as it falls. If the distance to the floor is 76 centimeters, then what's the smallest and largest angular speeds that cause the toast to hit the ground and then topple buttered side down? Okay? So, first of all, let's figure out how long it takes for the toast to fall. Okay? So the easiest way to do that is this. I know that my vertical velocity begins at 0. I know that my acceleration vertically is negative 9.8 meters a second squared. I know that my displacement vertically is negative 0.76 meters. So I ought to be able to use this guy to find the time, right? Does that make sense? So if you solve for time, you get, this is chapter 10 one, number 3. Oh, look at all the smiley faces I drew on this one. All right, so 0.394 seconds. So that's how long it's going to take the toast to fall. All right? So here's what I want you to do. So imagine the piece of buttered toast. The blue side is the butter. Okay? So if it falls and lands here, which way is it going to topple? The bad way, right? So how far did it rotate in that 0.394 seconds?
Pi over 2 radians.
Pi over 2 radians, right? A quarter of a rotation, right? So as long as it goes less than a quarter of a rotation, like if it lands and is at a little bit of an angle, less than vertical, then it'll fall the good way, right? But if it goes more than pi over 2 radians, it's going to, right? Okay, now, so that's pi over 2 radians, right? Pi radians, it just lands flat upside down. So if you go more than pi radians, then it's completing half of a rotation. So what if it goes 3 pi over 2? Then you're good, right? So during this amount of time, to land, it will land buttered side down if our change in theta is anywhere between pi over 2 and 3 pi over 2, right? Does that make sense, you guys? So that gives you your, so then you just do change in theta over t to find your two angular velocities. Does that make sense? All right, the tricky thing there is, and some of this is that we haven't talked about the different types of stability. So, I don't want to go into this right now. We can talk about this real quick. So here's your toast, right? If I tip it this way, it's going to fall this way, right? Okay. You guys know why? Yeah, because the center of mass goes past your pivot point. Like it produces a torque that causes rotation this way. Does that make sense? All right, let's do so. All right. That was your question? Okay.
That was your quest part.
All right.
I missed quest.
Do you?
No.
Honestly, so I felt like
Do ya?
good quest was very.
I like quest better than
like,
quest.
what
Do ya?
how much you got.
Say that again?
I thought that there are like condensed ways to like see like a really weird like variety of things. It's like a lot of like repetition. It's like generic. It had just like a bunch of really hard weird questions, but it got all the fundamentals done really well.
I'm honestly realizing some of that. I'm going to next year I'm going to print some of them up, I think.
I think it was good multiple choice.
I mean, there was a lot of
Yeah.
things just ended up.
I have come to the same conclusion recently. Okay, all right, let's keep moving forward though. And I agree with you guys that there is some value in it. I think that the format of it being computery was clunky, but
The problem was that if you got it wrong, you would take off points, so you wouldn't want to risk getting it wrong, so you just look it up on Yahoo.
right.
Yep.
Yeah. Yes. I'm not sure, like which side it lands.
Yeah, I think it's supposed to land butter side.
That would make sense, but there's more weight on that side. So,
So if it's flipping, you won't have any momentum on it, so keep going, it just even lands.
say that again.
If it's flipping, you won't have any momentum.
Yeah, I guess technically you would. Yeah, I think the problem's a little bit oversimplified in that sense. Yeah. Okay, so that was number 3. What's next on the list? 18? All right, oh, this stupid pulsar one. Okay. This one had some pretty involved calculus. I guess there's probably some value in showing you guys this. This might be. This is gonna, I think, be some like more challenging calculus. But that is okay.
We learned the air drift stuff today.
Oh, did you?
Yes. We learned the reading.
Okay, so here's what we know. It says a pulsar is a rapidly rotating neutron star that emits a radio beam the way a lighthouse emits a light beam. All right, it says we receive a radio pulse for each rotation of the star. The period, capital T, of rotation is found by measuring the time between pulses. The pulsar in the Crab Nebula has a period of rotation of T. It's got a period of rotation of T, so it's 0.0333 seconds. And it tells you that it's increasing at a rate of 1.26 times 10 to the negative 5th seconds per year. So what is that? I need to give this thing a name. What does this value represent?
No.
dt over t? Yes, I agree. D, what kind of t? The big T. It's telling you how quickly the period is changing per generic unit time. Yes. Sorry? Oh, I have an extra 3? Okay. Oh, I see. Thank you. Sorry about that, and thank you for putting that. Okay. So what we're trying to find is the angular acceleration. All right? So there's definitely a trick to this. Okay? So here's the deal, you guys. So we're trying to find angular acceleration, right? What's the definition of angular acceleration? So the rate at which the angular velocity is changing, right? Pretty good with that? Okay. So what the problem is I don't know anything about, how do I want to say this? Sorry, let me process this for 1 second here. Sorry, just making sure I think this all the way out. All right, so what we need to do, so this period is related to the angular velocity, right? Okay, so let's do this. So what this is telling us is that at this instant, our angular velocity is 2 pi radians over 0.033 seconds, right? Does that make sense? That's my angular velocity, right? Good? All right. I guess I probably should have just written this as, oh wait. All right, so that's at that instant. Sorry. All right, so in general, can I get away with calling that omega naught? Is there a problem where they change the time? I think this is one where they talk about. Yeah, let's call that omega naught. Call that T naught. All right, so but in general, omega is this, 2 pi over T. That's what I was trying to get at. Does that make sense? Right, so at a given instant, there's a period, right? And your angular velocity at that instant will be 2 pi divided by T. That was where I wanted to go. Follow? All right, so here's what we're going to do. We're going to rewrite this. Alpha is, I know I'm rewriting the same thing just because I have a little more room down here. So this is this. That's the same as right? If you cancel these, you're going to get what we started with, right? Cool. Well, look, I know dt is 1.26. So now I just need to differentiate 2 pi over t with respect to t. So this is, let's see, the derivative with respect to the period of 2 pi over t times dt over t is this number, 1.26 times 10 to the negative fifth seconds per year. Let me pause for a minute and let you absorb that. So the trick lies in rewriting angular velocity in terms of the variable that we're given, in this case capital T, period, right? So that was kind of the trick there, was rewriting dw d little t as dw big T, d big T, dt. Okay, all right, so we just got to differentiate this thing. So this is 2 pi times t to the negative 1, right? So the derivative of that is going to be negative 2 pi t to the negative 2, so over t squared, right? Follow? Times 1.26 times 10 to the negative fifth seconds per year. All right, so, and at this instant, we know what t is. T is 0.033, right? So just plug in 0.033 and you're done. So, right, is that what I did here? That's what I did. Oh, no, you're not done, because we got to get our units to jive, right? So when we get our angular acceleration, we're going to want it to be in, what, radians per second squared? If I leave things as they are now, I'm going to get radians per second per year, right? And that's not what we want, so we're going to have to do some converting here. All right, so let's see. So we're going to have negative 2 pi over, let's see, t is 0.033 seconds squared times 1.26 times 10 to the negative fifth seconds per year. So when I figure this out, I'm going to get the inverse of year seconds, right? So radians per second per year. So we need to factor label that into, so let's see, 1 year is what, 365 days. 1 day is 24 hours. 1 hour is 3,600 seconds. So that should give you your final answer. Sorry, it's kind of on 2 lines there. You guys read it? Should I begin it? All right. Follow? Yeah, Alex. No, I mean, that's definitely on the hard end. There have been a couple AP tests where I've seen you have to do similar tricks. It's not the norm. It does come up though, so I want to expose you to those occasionally. And once we get through everything, that's I think what we're going to focus on is some of the calc stuff. Some of these weird, like we talked about the air resistance thing and this kind of thing. So I'll make sure I give you guys some of those. My intent was to do that before the holiday break, but we just didn't have time. So. All right, does it make sense? Are we good up to that? All right, I think once you've got that, parts B and C are not bad. Part B says, how long will it take to stop rotating if alpha is constant? So, you know your initial angular velocity, you know your alpha, so, find the time to get to 0. And then part C is similar. I think once you've got that alpha, the rest of the problem is pretty straightforward. So, is that cool? Okay. All right, let's see if we can get one more in here. What does that say, 24? That's 24. And 27. Do either one. Let me see which one has less work on my paper. 24 is quick. Well, let's do 24. We didn't have time to do 27. 24 is pretty quick, and then we can put that video on there. Okay, so 24. A vinyl record is played by rotating the record so that an approximately circular groove in the vinyl slides under a stylus. Bumps in the groove run into the stylus, causing it to oscillate. You guys know all this, yes?
Yes.
The equipment converts the oscillations into electric signals and then into sound. Suppose that a record turns at a rate of 33 1/3 RPMs. 33 1/3 rotations per minute. So that's my angular velocity, right? The groove being played is at a radius of 10 centimeters. Let's see. Is there any reason why I can't just leave that in centimeters? Yeah. I'm going to leave that in centimeters. Let's see what happens. And then it tells us the bumps in the groove are uniformly separated by 1.75 millimeters. So that means that our delta x between 2 bumps is 0.175 centimeters, right? Follow? Per bump, right? That's the distance between 2 bumps.
I
Yes.
think that this is where the term groove, like V came
I
from.
don't know.
Oh.
I don't know. I don't know. Maybe. Okay, so any ideas about where to go from here?
No, it's jazz slang. Sorry, Kurt.
Oh.
I was about to just have a really good day.
Oh wait, the analogy is to the groove in a vinyl record.
Whoa, nailed it!
What happened on Friday?
Music
That was
is so
great.
together that it's like they're the needle guided by the groove.
Nice. That was really cool, Kurt.
You got it.
All right, so if you figure this out, this gives you 3.49 radians per second. All right. Why do you guys think I converted that to radians? Yeah, because we're going to have to use a jumper equation at some point, right? Because I've got some linear values and some angular values, right? All right, and what I want to do is I want to somehow convert to what? Bumps per second? Is that what we're trying to get? Yeah, we're trying to get the frequency of the bumps, right? So we want to get to bumps per second. So, any ideas? Yeah, it's honestly what it is. Let's do this. So we've got 3.49 radians per second, right? That's my omega, right? So I can do V equals omega R. Basically what I'd be doing there is multiplying by, what am I doing? 1 radian is the same as 10 centimeters, right? Does that make sense? That's V equals omega R. And so right now I'm at centimeters per second. So I ought to be able to, this is 0.175 centimeters per 1 bump. So that's the same as doing 1 bump per 0.17, oops, I got my decimal wrong spot. 0.175 centimeters, right? So yeah, it's totally just unit analysis, or dimensional analysis. What was the negative your answer? What was the answer on it? 199 hertz, 199 bumps per second. Alrighty. Okay, have a good break, you guys. 3-4, 3-5 due on Tuesday after break. We'll spend some more time with this when we get back to refresh your memory about what we were doing, alright?